pin. But I guess if I pin video, it's only for myself, so it doesn't change anything. Okay. Yes. So today we will talk about streaming algorithms, and there are two reasons for this. First, students told me that this year one student told me out of the selection of one student, I asked what he need, and he said that I do something close to streaming algorithms. So I would like to hear this. But another year I also did a very small check, and also so surprisingly, people actually use the streaming algorithms. And the second reason I will speak about it is that in streaming algorithms, there are problems where we can have full upper bounds and lower bounds, at least on memory use. And they use communication complexity in kind of simple form. And so for theoretical computer science people, they're like a toolkit, and each tool separately is already a struggle. So it's nice to have a place where you can use a single tool and do something with it. And so it's possible for lower bounds in streaming algorithm, because like everything is connected to everything. And it's very interesting, but it's like a really nice step. And so next lecture, I will use lecture notes of Tim, what is his name again? Roughgarden. I hope I say it right. Tim Roughgarden. And there he proves that algorithms we will discuss today are optimal in all possible senses. So any bound we have today cannot be further improved. Okay, so let's first start with a streaming model. So there are inputs. So we will receive a bunch of numbers, first motivation. So streaming algorithms, that is for when you have to deal with a huge amount of data. You should think about inside the router, like you're flooded with packages, you need to get them out of the way, no chance to store the data you have there. And the goal is to collect statistics from the data. For example, if there is a heavy hitter, that means that if there is an element that's repeated, for example, in the router you have IP addresses and you want to know whether there is like a certain out of service attack, like the same destination is asked many times, and people want to know about it, I guess, to stop attack. So it's heavy hitters problem. Other applications, I think a profiler is a nice application. But all these books have like long discussion about application. I don't think it's so convincing. I think that in streaming algorithms, like you're pushing the memory down, and it gives like many indirect other advantages.
So we have a constant memory.
Yeah. So we will have a logarithmic memory. So but our input will be linear, so we cannot store the input. And we will see our input only once. So it will arrive, and we need to remember whatever we need. Okay, so input is a list of integers, and they belong to the set integers bounded by m. So remember that this is the set 1, 2 till m. And then there is a second parameter that at some moment we will we will receive the nth element, and we are interested in a certain function from first n elements. Okay, so there are two important parameters, n and m, and we want to have algorithms that are logarithmic both in n and m. So these numbers, of course, they can represent strings, and then typically little m is a power of 2. Okay, that's a model. And then there is like famous interview question. So, yes.
Wait a second. And M is given in binary or
Yeah, so usually M we know in advance. For positive results, we will not know N. So we will say, okay, now you've seen everything. Please tell us the answer of the question we
yeah, okay, but you say that we want logarithm in terms of M, but M is unary or binary representation.
So M is an integer, and the memory can use will be log M plus log N, order log M plus log N. Okay, so first problem is that we are given a sequence of numbers, and one number appears at least half of the times. So this kind of promise problem, our sequence contains one number at least half of the time, and then can you give an algorithm that finds this number yes. There are okay, let us speak about some simple problems. For example, we receive numbers, then it stops, and we want to know N. This is a problem that easily can be solved in space order log of N. We just have to count. It's a trivial example. Okay, but so now let us go to this problem called happy hitter. So we're promised that at least half of the elements are one single number. The other half can be anything else. How can we find this number, this single number, using logarithmic space and memory? Know that if we could use if we could use space n log m, for example, or m log n, then we could easily count everything. Or store everything, and then it would be an easy problem. So
could you repeat the problem, please? Which single number do we have to find?
Yeah, so you're given a stream, and yes, and we know that at least half of the elements in this list is the same value. So each element is a number, and the same. For example, let's do example like 1, 5, 2, 3, 3, 5, 3, 2, 3, 3. So how many numbers do we have? 2, 4, 6, 8, 10, and we have 5 3s. Okay.
So we need to output 3 in this case.
Yeah, let's say more than half. More than half of the appearances are the same number, and then we need to output 3. So
okay, thank you.
Yeah. And so when we come here, algorithm ask output 3. This is kind of interview question. At least that says Tim Roughgarden in his book. He writes that this is popular interview question. So how can you find it? And maybe somebody has learned this already. Okay, so we will have a counter and a buffer. So counter and buffer is algorithm. And the rule is that if buffer is empty, next element goes into the buffer and counter goes to 1. And then if you see an element, so this first rule. Second rule, I will write it later. Second rule, if you see an element that is in the buffer, increase counter by 1. And third rule, if you see an element that's not in the buffer, decrease counter by 1, decrease by 1. And if counter is 0, make buffer empty. So this is the rule. Let me write it. So if buffer empty, then next, so an, let's say that a next goes to buffer. Second rule, if an equal buffer, then increment counter. And third rule,
Probably better to write a next. Okay, sorry. Okay,
yeah, sorry. And then, by the way, the marker is not so good, but I guess you can read it, okay?
we can hear.
You can read it, right? Okay.
Now we can read. But I don't see the word if. But
Yeah.
it's pretty.
Yeah, that marker. If a next not equal to buffer. So these are the three rules. Okay, and afterwards we have to stop, of course. So then we are finished. When we do a rule, we are finished. Stop. And then the last rule, actually, I don't need to check here anything because.
Wait a second. You said that we don't know when the string is finished and a certain time was where.
Yeah, I still need to tell you what's our answer, but answer will just be what is in the buffer.
Yeah, you just say stop,
Yeah.
but it's not.
No,
not
just
our-
go to the next. Yeah, okay, I can write next. I mean, just do 1, 2, 3. So for each.
So basically, you're saying that we on each iteration we have one of three cases.
Yeah.
Yeah. Okay. So just stop is ambiguous.
Yeah. Okay. Yeah. I should say okay. Do one next cases and third. Okay, I will keep not so efficient. Next, not equal to buffer and decrement counter. If counter is 0, empty buffer. Okay, so we do exactly one of these lines. And I forgot here set counter to 1. Okay. So let us see what's happening here. So here we counter buffer pair will be 1, 1. Here we will have, after processing 5, we will have, so we are different here in the last, so we will have 0 and empty. Then we will have 0 and empty. We will have, sorry, after processing 5, it's not right.
Yes, because 0 and everything and each other.
Yeah. No, my algorithm is not right. If a okay, this was if buffer is empty, okay, set counter to 1 in the last 0, and here set buffer to a new element. So basically, we have to do this rule again. With 0, do 1. So, okay, now it's right. Sorry. So go to 1.
So at each point, the buffer is not empty.
Yeah. So after processing each element, yeah. So here we will have 5, 1, 2, 1, 3, 1, 3, 2, 3. So after 5, we have 3, 1. Then we have 3, 2. We have 3, 1. And so on. Okay, and now to see that this works, you already understand how it works. And so each incremental buffer we can match to each decremental buffer we can match to corresponding increment. So this creates a matching between elements. So the sum of the elements.
You're creating the matching between like the repeating elements and some not repeating elements.
Yeah.
Okay.
So for example, this 3 and 5 can be matched to each other. So when we saw this 3, we go from 1 to 2. When we see this 5, we go from 2 to 1.
Okay.
And so these elements get matched. And
the first two numbers we have.
yeah, there is.
Yeah, we can match them with the like last elements. And since we have
Well, we just say that some elements have a matching, we don't care about the other elements. And now we want to say that in the end, we will have positive, we will have the majority element inside the buffer.
yeah, it's just because like because the fact that it's at least half of them.
Yeah,
Like half plus one.
yeah. And so in order to get rid of an element, we need to match all its appearances to previous elements.
It's impossible since it's this element appeared. Majority.
Yeah, so here we go from, so you're right, we need to match. Okay, this is so easy, I didn't prepare and now,
I think that's.
yeah, you're right, yeah.
First algorithm
Was
you
right?
understand it was right, yes.
Ah,
Because
okay.
we don't increment or decrease or increase every time when the right number.
Didn't see this problem coming. So empty buffer. And you say that it's also wrong. Okay, let's check. So well then we will have here. Then we will have like we will have 0 and
empty. Then we have 2, 1, 1. Then again 0 empty.
and 0. Empty.
Then 3, 1. Then again 0 empty.
Oh, sorry.
That's something. Then 3, 1. 0 empty. 3, 1, 3, 2.
1 and so on. Now I'm adding.
I'm not convinced that it's working this time.
Because every time we use the number which include lines, we plus 1.
No, let me I think I have like a control example. Like imagine you have something like 3, 3, 3, and then one element. Then you have here 3, 1. Yeah, 3, 1. Here 3, 2. Here 3, 3. Yeah. And then you have like 0 empty because it's
No,
not
no, the 3, 2 you had.
Why? If you have like
Next decrement counter. And if
you
counter
count
is
0, okay.
so decrement by 1.
So,
Yeah. No, I think you're right. It's nicer algorithm. So
Because every time when we use the one or the number we use, most times it decrease our counter. We can set them every other numbers to increase for
yeah.
I'll say
Yeah, so each time we have a decrease, we can also have the matching. So it's also matching.
Yeah, okay, and
It equally works. Yeah.
in the case when we have like half elements 3 and half elements 2, we should say what we should say.
Well, then we can have like all ones, half ones, and half twos, and then we cannot say anything because there is no majority element.
Oh, so
Yeah.
we need like
More than half.
more than half.
Yeah. Okay, but I cannot think. I will try to think again. So each time counter, and so here we have an increase of counter and a decrease, and after the decrease it's empty. Yeah, and it also works. Yes.
And we can do it easily if we now use one another counter of threes, or another counter which counts the number 3 that will count n divided by 2 plus 1 time. So we have n divided by 2 plus 1 pluses and this n divided by 2 minuses.
Yeah, at most. Yeah. Yeah. I agree. Yeah. So let's look to the trees and then.
But could you explain?
I'm confused. Yeah.
How do the matchings help us here? So I understand it intuitively. How do we get 3 in the end in this case? But
Yeah. So, but the example is not so nice because we never match. We always match to the next one. So let me change the example a little bit. So imagine that.
yeah, just like with this example.
Yeah. So for each increase, so imagine that we have a certain number in the counter. We have a symbol in the counter. So okay, let us
Overall, we don't need to know how we connect the increases and decreases. We need to know the majority of all case is give n divided by 2 plus 1 pluses and other numbers give at least, but at most n divided by 2 minuses. So our will have
so your argument is we must have more pluses than minuses because we cannot have negative numbers.
No, it's like the opposite. We want to have negative numbers because we surely have more pluses than minuses. Just from the statement that we have a majority of elements. It's true. Well, because for each repeating element, you have you're increasing the counter and if you have not repeating element, you're decreasing. So it's like the statement.
Well, so that's how I view it. So let us look to the counter. So it might go up and then it might go down and it might go up again and go down. And so each time we go up and later, so each time we go down, let's look to the last time we went up. Okay. So then let us match these two elements. These get matched. So here we go again down and let's remove the matched elements. Now when we go down again, let's match this element with the element where we did the opposite movement. So these get matched and let's delete them. And then we do this each time. Each time we go down, we match it with an element that goes up. And we know each time we match two elements, they are different. And so after we removed all matched elements, we know that the only element that remains is the majority element. And therefore we know that the pluses, only the majority element remains, And this is precisely the value of the counter we get at the end with the buffer. That's how I understood how it works. And you are right, with this algorithm it also works. But I must say that I'm confused myself now. It's yeah. So, okay. It should be fine. But when I'm a bit more relaxed, I will think about it again. And we can discuss it again in the beginning of next lecture. Yeah, I just think that adding the element right away, it feels like it should help. Because then, but when we add it with the, okay, I should think about all variables and which one is the best. But okay, let's, so this is for heavy hitters. And maybe it will just help if you solve it more generally. So you can have, if you have at least a fraction. So imagine that you have streams and there are k-1 numbers that appear at least a fraction 1 over k. Then you can do something similar. It's in the seminar exercises. I should solve it myself for sure. But okay. Yeah. So this is for heavy hitters. Now let's look to another problem. So now we are interested. We will have m equal to 2. By the way, so the size of the algorithm is order log n plus log m. This memory is needed. This was clear, right? Because just counter and buffer use this space. Okay. So now next problem, we will have m equal 2, and the plan is there is a number t, and we want to know, so that we have zeros and ones, and we want to know the sum of the last t bits. So t is fixed, and we want to know sum of last t bits. So for example, if the sequence is 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, and t is equal to 3, then when we are at this place, so when we are at this position, we want to know the answer 1. If we are in this position, we want to know the answer 3. Okay. So, and there is algorithm that runs in space. Okay, marker is not working. Log squared. Oh, but by the way, we can have approximation algorithm for this problem. I didn't read it anywhere, so but I think it's so. This gives us a 1 plus 1 over k approximation with order k log t memory. Well, how can we? What is this algorithm? Oh. Oh, sorry, this is not true. It's not the 1 over k approximation. So what I want to say that there exists a streaming algorithm, so that let Sn be the Sn be equal to the sum of the last t bit. Okay, and so then I claim that there exists a streaming algorithm that such that the streaming algorithm of A1 till AN is right up to k over t. So Sn is bigger than the streaming algorithm. And the memory use is this one. Sorry. There exists an algorithm for all n. So the answer is streaming algorithm E1 till n is at least Sn minus T over K and Sn. Okay. And so what is the streaming algorithm? So if it's right, up to a shift T over K. And the streaming algorithm, the idea is that just you start K counters every T over K elements. So, for example, T is equal to 3. Okay, we need a bit more. Imagine that T is equal to 6 and K is equal to 2. Then we just start a counter that starts counting every 3 elements. And then you output the maximum of the counters you have so far. And of course, if a counter is too old, if a counter was started more than T elements away, then you drop it. So it's a very easy algorithm.
So what is K?
So K is parameter, for every K, there exists a streaming algorithm that achieves this and has memory K log T. It's kind of silly argument. I was just reading an old book, but in this old book, they wanted something more. They wanted a relative error 1 over K. So they wanted to have that the streaming algorithm minus Sn is smaller than Sn over K. This is a harder problem. Okay, how K1, comma Kn is smaller than K. And so how can you have this one? And the plan is to have to maintain a bunch of windows that increase geometrically. Oh, by the way, and the streaming algorithm uses space log squared of T. So that's the space it's used. And the plan is to maintain order log T of windows whose sizes increases geometrically, each double. So there are a bunch of rules. So maintain, and the sizes, I mean, actually the sum of ones in each window will double geometrically. So for example, in this sequence, imagine that the bits arrive from the right. There will be, so the rule is that for every size, so every size should be a power of 2, and for every size, we have 1 or 2 windows with this sum. So for every window, we look to the sum of the bits. So here we have just a window of 1. Here we have 2, and then okay, I need a bit more ones to make it interesting. So maybe this will be a window of size 4. And so we just remember the start points of each window. If a start point is more than T bits ago, if the start point was older than T bits, we forget about it because it's not relevant to us. And our estimate will be the sum of these 2 windows. By the way, sorry, it's a bit weaker, this Sn over 2, but I will later explain how to get a better result. So I will explain special case.
Can you repeat it?
Yeah, okay. But I just said the vague idea. So we maintain certain windows, and the sum of the bits in the windows must be a power of 2. And we each time remember the start point of each next windows. Windows are non-overlapping. So that's the idea of the algorithm. And now I have to explain how we maintain the windows and why the sum of the windows that we maintain is satisfy this bound. And so actually we have something better. So our algorithm will give a lower bound. So we will have something like it will be bounded by Sn, and here 1/2 Sn. That's what we will achieve. Okay. Yes. Okay. Maintain windows. And there are certain rules. It should be non-overlapping. So from right to left, the sizes should increase. It should be non-decreasing. Non-decreasing. And powers of 2. Then each size, of course, up to a certain level, each size should appear 1 or twice. Each size that's a power of 2, once or twice.
The size should be powers.
Yeah, the size should be power of 2. Let me give an example.
So, like there can be 2 windows of the same size and not more.
Yeah, but no more. So that is.
But you said that the size should be not decreasing right to left, but there is a decreasing size right to left on the example.
From right to left?
No decrease.
So then.
Oh, okay. Yeah. It's
we have
increasing.
Ones, twos. Okay. And so every window should lay in the last t bits.
Yeah, you're saying that each size should appear once or twice. Can it not appear? So can it be
Yeah, zero. Well, I mean, 0 only if they're very large. So at some point when there is a 0, all next sizes should be 0 times. Yeah. So the size, so from left to right, we should have once or twice. And when we have 0, all next sizes should be 0. So we have 1, 1, 2, 2, 4, and then let's say it stops.
And how to decide how many you will choose the same size?
So for example,
And can we, for example, okay, let's look from right to left. We have
so that might be the window, and then here we have, and there might be some bits that are not in the bin because the start point of the bin is too old. But we covered it, and so the plan is to cover the bits and bin in windows.
let's look like from right to left.
Yeah.
When we have like first time there's a window of size 2.
Yeah.
The next window, how can we understand it? It will be again a size 2 or a size 4?
So that, sorry, I mean, but size, I say sum of bits is 2. Yeah, so I use a bad word. I should not say size, but sum of bits everywhere. Right, sum of bits. And each sum.
So actually, you're always when you say size, you're
Yeah, I did some. Sorry for that. Okay. And so our estimate will be the sum of all the.
Again, I have a question. Like, okay, we have a window with the sum of bits 2.
Yeah.
Then we have like a prefix, some prefix. And how can we decide we are building the window with sum of bits 2 or 4? Like we have two options. We can maintain the window with
Yeah, we have two options.
and how we can and how
Okay,
we-
I didn't say it yet, but okay, I will explain now because you asked. So, but first, so we need to agree on the rules, that the rules are clear. So each power of 2, we see once or twice, and when we see it 0, it means that all larger sizes are forbidden. Sums are forbidden. Okay, so now imagine that there comes a new element. When it's 0, we don't do anything because no problems here. So we should, or we can like increase this one like this if you want. Okay. And then the last one, the window moves, of course. Now imagine there appears a 1 here. Then we are not allowed to start with the window of size 2. So we will make we put it in a bin of size 1. But now we have a problem. There are 3 bins of size 1. We just merge the next window. So we will merge these 2 windows. It becomes a window of size 2. And so we are good for the windows of size 1, but we have 3 windows of size 2. So we again merge one of the windows. We merge the 2 last windows. It becomes a window of size 4. And now we are good because there's only one window of size 4.
Memorize the size of window.
Yeah, we can memorize it. It's no problem. So per window, yeah. That means per window, we need log t bits. Plus, we need to remember its size, which is log t.
Why do we need to remember the size of the window? We know the sum. We just can't like look
Yeah.
to the
We
next
need to
bits.
remember the size because we need to tell what is the estimate of our algorithm. And it's the sum of these sides. I mean, I keep saying sizes, but you understand. It's the sum of these numbers here.
I'm confused. Like when you say we need to remember log t bits and log t.
Yeah, it's this number.
It's not a size. It's still a sum of bits.
Yeah, the sum of bits, yeah.
Okay,
So
and what?
we remember start point, like how many places ago, and the sum of bits in the bin.
Okay, and what is like the first log t in the complexity?
Log t is start point, and here is sum of bits.
Oh,
And it's log because it's power of 2. Okay, so it's clear how to update. So allowed sizes, allowed sum of bits are powers of 2, subsequent powers of 2, and each power appears once or twice. Okay, so now we understand why this is true. Because what we see here, we know that maximal number of bits that we can miss is the next power of the highest bin size, -1. Yeah, so here we have a bin. So in this example, like the window starts here and of course in the beginning. I mean that this is the heat last bit, for example, and there is just one place that's not in the bin. It's a 0, so it doesn't matter. So here was the previous bin that's now ignored. Might be 4 or 8, well, probably 8. So this bin is destroyed, and so some ones are not in the bin. But we know that the number of such ones must be less than the bits here. Because the powers are increasing. And the bin that was destroyed can be at most of size 8. Of sum of bits is at most 8.
why not 4?
4 is possible, at most 8.
No, why it can be 5 or 6 or 7?
Because that's the rule. the sum of bits in each window is a power of 2.
Yeah, I understand, but like there's some, well, we know that sum is appears once or twice. We understand that we have twice appearance of 4. Yes.
Yeah.
And we have some all bits.
Yeah, so here can only be a window. Before this, the window that was discarded,
It's 8.
it is 4 or
It's
yes,
can be
it can
4.
only be 8. Yeah, yeah. In this case, only be 8. But then we have moved the window at least once, so it must be less than 8
Okay.
that are still not counted. And since we have all the powers, their sum is also less than 8. And their sum must be at least 8.
Mhm.
So that means in the bins, in the windows, we have counted at least half of the ones. So every power needs to appear at least once. Yes. So their sum will be 1 less than the next power, at least 1 less than the next power. And the number of ones we discarded is also less than the next power. 1 less than the next power at most.
So we discarded at most
Half of the ones in our count, and so this is proven.
Mhm.
Okay, and now everything is explained.
Could you remind, please, what are we expected to output?
Yeah, we are expected to answer this condition. So Sn is sum of the last t bits, starting from the position n here. So Sn is just the sum of bits in this window. So after we received n elements, n bits, Sn is the sum of the last n ones, and our output should be at most Sn and at least 1/2 Sn. So that's the task. So is task clear? And then the
So
answer,
we
yeah.
have to return some number that is between Sn and 1/2 of Sn.
Yeah,
Is it useful somewhere?
I don't know. I will tell you for what it's useful. So now we looked at, well, you should think about an alarm. So alarm goes off and you don't care if it's rare, but if it happens a lot, this alarm, it might be some attack or whatever inside the router or might be something similar. So
What is our alarm?
maybe, yeah, so something bad, it may be in a rocket or something, whatever Elon Musk has.
No, you mean it's just the motivation or it's
Yeah, that's I ask for motivation. So what does the bit represent? So that's first explanation. Maybe you want to know.
Yeah, just the problem just looked for me some unusual.
Yeah. Or maybe
Okay.
teacher, he receives homeworks online, and if suddenly if there are few bad grades, he doesn't panic. It's just student who has a bad day. But if suddenly he receives many bad grades, it means he is doing something bad. He needs to explain better. It's another example. Okay, this is first motivation. But second motivation is we can extend this algorithm. So imagine that now instead of bits, we get numbers. And we want to maintain the sum of the last n numbers, of the last t numbers. Then we can do something interesting. We want to have an estimate. So now Sn is the sum of the last t numbers. We can have the same result, but here with the bit size, with x subfactor log m here. And already know how you do it. It's very simple, clever trick.
So can't we just intersect this idea with the first idea when we have buffer?
No. We just look at, so we put the numbers in binary, and for each position, we get the bit sequence for which the sum satisfies this result. But then when we have, for each digit, the precision of sum with precision 1/2, then we can add up the sum. So what do we get? We get a bunch of numbers. And if we look, so this is A1, A2, A3, A4, and so on. Now we look at the column, the least significant bit, and we get the sum with precision 1/2. Then for each position, we get the sum in 1/2. So then we add it back. So each sum we add up with appropriate power of 2 to get the sum with the same inequality. So just a linear combination of this thing. And so we can make it. So I think it's very clever algorithm. I never, so it's from old book by Ullmann. I will put a reference in, and it's not yet on the wiki. I will put it there. Yeah, a book is called Mining Massive Data Sets, and some other teachers were using it. So that's how I found this book. And yeah, okay. So this is the first two goals we already had. Yes. Oh, sorry. Yeah. A lot of attention. So let's go to the next topic. Definition of frequency moments. So frequency moments, there are certain statistics, and they're at huge attention in research. So I assume that there is, and I will explain what they are, and then I will motivate them. A1, A2, and so on. And this remains the same. And so we have the count of I is just number of appearance of number I. So it is, okay, let's write it in the mathematical definition. It's the size of the set J for which Ij equals I. And then the frequency moment Fk is a sum of Ci to the power k for I equal from 1 to m. So these are frequency moments. And we also do this for k equal to 0, and we use the convention that 0 to the power 0 is 0. Okay, so let us look to some frequency moments. So the easiest one is F1. So F1 is just equal to the length of the stream, which is n. And so we fix a certain moment n. After seeing n bits, F1 is equal to n. Then we have F0. So this is completely uninteresting. At least it looks so. So it's the sum of the counts of all I, yeah. F0. So what do we count here? So we take a number, positive number to the power 0 is 1 always. And this is number of different elements. This one is really important. For example, there is a movie on YouTube of a guy on Facebook, and his responsibility is for each message, count how many different people have seen the message. Like if what's the fraction of people that press like or whatever, you need to know how many different people have seen it. But then naive way is just like every Facebook user has a number, is to, for every message, store the list of people that have seen it. But it's a lot of that. I mean, to maintain such a thing, you need distributed database and so on. So for every message, he needs to compute F0. And so we will see, in the rest of the lecture, we will speak about approximation for F0. Okay. Then the next one is F infinity. F infinity will be, okay, this power is a bit, so this definition doesn't completely work, but people define this as maximal frequency. It's connected to heavy hitters problem.
It should have been working as norms, but something wrong.
So I just using convention of all the books and papers that they're pretty consistent with this. So yeah, of course we should take root k and then it works nicely, but this is definition. And this one is very difficult to approximate. By the way, in heavy hitters problem, we considered the problem of finding majority is, so here we find majority element assuming it exists. The problem of deciding whether there exists majority element cannot be solved unless you have you use space or small, so you need space omega minimum of n m. So why is it true? Well, imagine that first half of the sequence are all different elements. So the moment you have processed first half, then existence of majority element depends on the second half. And you need to store precisely which elements you have seen in order to solve this problem. And that means you cannot do it with memory less than so you have to store the full sequence. And so for this you need at least a minimum m of m comma n. So for example, if n equals n, if n equals 2m or something, if n equals 2m, then you store half of the set. But that's a lot of sets. And if your memory is just for two of such sequences the same, then you are in trouble. You cannot decide the majority, whether there is a majority element exactly. Okay, so this heavy hitters problem is kind of interesting. So you can decide whether there exists majority element, but if it exists, you can find it with logarithmic space. Okay, and this is why F infinity is a difficult thing to deal with. But remarkably, F0 and of course F1 and F2, you can like estimate efficiently with a probabilistic algorithm. So that's what we will be doing now. Okay, so first we will estimate F0 with high probability up to a large constant factor, so up to factor 6. So let us explain the idea of the algorithm. And before this, I will speak about something mathematical. Imagine there is unit interval, and somebody draws random points in unit interval, d random points. You don't know d, but the person tells you what is the minimum value of the points. So x1 till xd. So somebody draws an unknown number of points that are uniformly distributed inside the interval and tells you the minimum of these points. Then you can use this minimum to estimate how many points there were drawn. For example, if this minimum is equal to 1000, you can expect he draws many points. If this minimum is whatever, 1/3, you know he only draw a few points.
Yeah, so it's just basically creating indicator functions, and we're we can just forget the left side, left side and replace it by manual.
We can forget. So the idea is that expected value, I don't know the proof of this, but this expected value book says that this is equal to 1 over d plus 1. If you draw
just
this point.
from the statistics.
Yeah.
If you want to like, well, okay, it's not natural.
Yeah. So knowing the minimum, you can know how many. So what will be the plan to estimate F0 number of different elements using very few memory? We will use a random permutation, let's say from M to M. So H is a random permutation. And we will look to the minimum value of a point that appears. So what we will do, we receive sequence A1 and we compute H1 and we look for the minimum of AH1, HAN. And I guess I need to change the marker again. We need the minimum. But here we have random permutation. So, and this will be equal to, and then as estimate, so if the minimum value is equal to V, then our estimate will be our estimate of numbers will be so SA is just M over V. So if V is very small, we get a large minimum, we get a large estimate.
So wait a second, you're taking the random permutation of this this forest, yes?
Yeah,
Then you say that the minimal element for after like applying the permutation is something called V, yes?
yeah.
And then you are saying that there is a streaming algorithm with the approximation M divided by V, or what is it?
So with high probability, M divided by V will be equal. So, okay, the lemma is that M divided by V is equal to F0 within factor of 6 with probability 2/3. So let me write the lemma here. Yeah.
And the distribution is uniform.
Yeah, so we will take a random permutation. Okay, a random permutation we cannot store in the memory, but I will later explain how to deal with this. I will also later explain how we get epsilon approximation instead of constant vector approximation.
Question: can function be in the same point?
Collide.
Can H or A?
Yeah. So I will H is kind of secret name. It will be a hash function and it will have no collisions because we go from M to M.
Okay. So basically, because of this, it's a hash function. We can split.
Yeah.
No, we can store it.
So we will use finite field and then take
Yeah,
a
like-
random linear function, and we will need two wise independence, pairwise independence hash function.
How will you construct hash function with no collision?
Just linear function, and we exclude coefficient 0.
Okay.
Maybe we even don't need to exclude coefficient 0, but okay. For now, I'm explaining the idea. And let's now put a lemma here. Oh, because we don't know.
So, and what is M like in the statement of interval? And
Yeah, this,
no, but here, what is M?
yeah, it's the same. So we get, we know the, so M is known for the streaming algorithm, knows the upper bound on the numbers it will receive.
Yes, but here we have only like interval from 0 to 1. M can be bigger.
No,
than
no,
1.
this is just a start. So now let's forget. Okay, we can have an interval from 1 to m integers now.
Okay.
It's the same idea.
Yeah, I understand, but I just want to also you can just build a with projection from 0, 1 to
Yeah.
I just want to understand what is what.
So that's why we have to use m divided by v to estimate the minimum instead of 1 over v.
Okay.
In the 0, 1, we had 1 over.
I see. Okay.
So lemma says with probability 2/3, we will have f0 times 1/6 of f0 is equal to m over v is bigger to 6 f0. Okay, so v is defined here, it's the output of our algorithm. Okay, so we have two troubles. Okay, three troubles. We need to prove lemma. Then I need to tell you how to get rid of a fully random function and go to a hash function. And then I need to get explain how we can improve these bounds. And in the seminar, you will learn how to go from 2/3 to 1 minus delta. And it costs you a factor ordered log 1 over delta. So these are the tasks. So first task, let's prove the lemma for like a perfectly random permutation. So one of the bounds is easy. This is the, so we first say that our estimate cannot be too big. This one is easy to prove. So what does it mean that our estimate is big? It means that our value v is very small. The minimum is very small. It means that for some element, the function is really small. So so let us look at this bound. So I claim that the probability that there exists an I such that HAI is bigger than 6 times that m over HAI is bigger than 6 f0 is smaller than 1 over 6. So that's what we will prove. And so what does it mean? Let us look here. This event is equivalent to m over 6 f0 is bigger than h over AI. And so now it's probably already clear why this is true. So what are we doing here? We just we know that in their sequence we have f0 different elements. Let us look at one element. What is the probability? That's so fix I. What is probability that h of AI is smaller than m divided by 6 f0? So what can we say about it? How can we say that this probability is small?
And the f0 is the number of different elements.
Yeah. But know that h of I is a random value between 1 and m.
Yeah, so that we want that
Yeah, so what upper bound do we have? So it's
just
so
behavior, like
1 over, it's easy question. So it's just 1 over 6 f0. So here we have m elements. Probability that we are at most 1/6, 1 over 6 f0.
okay.
Yeah, it's so easy. Okay, sorry for mark. My last one. So 1 over 6 f0. Okay, and but this is for fixed I. So now we have to go over all I. And so here we look at how many different elements are there. Of course, if there is a repeated element, it doesn't contribute to the probability. So number of events we consider here, it's a union of f0 events. Each event has probability distinct, so we just multiply by f0. And so this one is okay. This one is proved. Okay, now let's prove other bound. Okay, are there questions? Can I remove it? This is really proof. Other proof is also not so difficult. Now we are interested in probability that the minimum. So here we check that the minimum is large. Now we want the minimum to be check that the minimum is small with only small probability. So for all I, m over HAI is smaller than f0 divided by 6. We want to bound this probability. We want to say that it's smaller than 1/6. Okay, how can we do it? So now did I do something wrong? So we have two inequalities. We proved this one, this violated with probability 1/6.
Yes, okay, yeah.
Now we will prove that this one is violated with probability 1/6. And so we need to prove that yeah. And so V is a minimum. So we have, okay, I should just let's do it in a few. So I'm also tired. So let's turn this one around. So we want V smaller than m by f0 times 6. And we want this to be violated, but this is the minimum. Minimum of HAI. This smaller than 6m divided by f0. And we want this to be false. It means that the minimum is, yeah. So the opposite. So opposite is that minimum. Minimum of HAI is bigger than 6m over f0. It's not the opposite, but like if I prove that this happens, we'll prove that this happens with probability at most 1/6. So I will prove a slightly stronger that this has probability at most 6. So the minimum is bigger than 6m over f0 if for every I HI is bigger than, now we can turn it around. HAI is bigger than M6M over M0. So this is what we need to prove. Okay. So let us check what is probability of this event here. It is 1 minus 6 over F0. Okay. But it needs to happen for all I. Since we take a random permutation, oh, that's not independent. Okay, but sorry for this. Let's just take a random mapping from M to M, not permutation. I never use that it has to be permutation. Yeah, I never compare two variables. Okay, so take random function here. And then we have, we can compute this probability very nicely because it's F0. So values are independent, each next value. So here I used union bound. So it doesn't matter whether events are independent or not, but here it's important. Okay, and now we can bound this. We can bound this first. Let's apply a trick. Let's divide by 6 and then take to the power 6. And here this is bounded by exponent of 1, minus 1, sorry. And so this one is bounded by exponent of minus 6, and this is smaller than 1 over 6. So we have proven the lemma. We've proven that each equality is violated by at most probability 1/6. Okay, cool. So this is our first task, prove the lemma. Second task, get rid of function h. I said we will take hash function. So
exponential of what?
Minus 6. So yeah, I write to the power F0, I wrote as F0 divided by 6 to the power 6. And this thing is exponent 1, at most exponent 1. Minus 1, sorry. So lemma is proven. Okay. So it's clear what is our streaming algorithm. We take random permutation, we check all the values, and remember the minimal one we've seen so far. Value of minimal 1. But there is a problem because we will pick a random function h and we need to store this function. I mean, and h takes m bits or m log m bits. So how will we solve it? The plan is to use two-wise independent randomness. Oh, but the lecture is finished now. I was way too slow today. Okay, yes. So then, as usual, let's talk 5 minutes more. So our plan is to use a function that is pairwise independent. And for our proof, this the first part still works, but here we used independence. And so we are in trouble now for the second part of the function. So we know that if we look at at several different variables, they're no longer independent and we cannot multiply it. What will rescue us is Chebyshev inequality and an observation that sum of variances of pairwise independent variables is equal to variance of sum. So variance of sum equals sum of variances. But for this, we only need pairwise randomness. And in Chebyshev inequality, we can apply pairwise random.
You mean pairwise independence?
Yeah, yeah. So this is the global plan, so I must delete this part. Okay, and to make space, I will delete this part. Now we have Chebyshev. This is our main idea, probability that y minus expected value of y is at least t is bounded by the variance of y divided by t squared. And also, the second thing we use is if x1 till xn is pairwise independent. And so it means if we take any two variables, we can assume they are independent. But if we take three, we might be in trouble.
Yeah.
Then the variance of x1 plus xn is equal to the variance of x1 plus variance of xn. So these are the two things. Did you prove this in your statistics course? It's just calculation, right? So to prove it, you can use centered variables for which expected value is 0, and then you just have to look to x1 plus xn squared. So that the variance of this thing is expected value of this thing. Then you work it out. And you know that terms like x1 or x2, they will be 0. And only the terms remains where the two indices are the same. That's all. And say assume a centered variables because variance don't depend on shifts. And then work out this and you get the right hand side. Okay. Well, so here we will use two-wise independent randomness. What does it mean? The two-wise independent hash functions. It just means that if you fix any two arguments, the variables are independent. It's precisely what we need for this thing.
Mhm.
And now we can rescue our inequality. So we have to bound the probability that this happens. So we have to choose the variables xi, and xi will be the indicator function that for the ith element, this will be violated. So it just means that h of ai is I'm sorry, the minimum is bigger than
So the minimum is bigger. It means that that sum is bigger. So exists I such that it's bigger than 6m divided by m.
If you want to violate, you go back to less. Or
yeah, sorry.
Oh, no,
Yeah.
not exist. It's for all I. If we want to violate, we want to say that for all I,
Yeah.
minimum is greater
Yeah.
than.
The minimum is less than m divided by epsilon. Sorry, the opposite indicator of opposite event. Okay, and now we need we want to apply Chebyshev, and y will be equal to the sum of all x, y.
So wait a second. I thought you want the indicator of violating, but violating is the opposite. And you're right. You have written the opposite to opposite, which is
Yeah. I can choose xi, so I
Yeah.
choose it to be this thing.
I understand, but I thought you want.
Okay,
You want
the
to
opposite,
violate.
you want strict inequality, right?
No, I thought you want to violate.
No, let me speak. So I smaller than n. This is the same. And now I want to bound the probability that y equals 0. So if all x's are 0, then this event happens. Okay? And so now I should have used the strong form. Because then I have this inequality I needed.
So, but if we have all 0, then it is false. The probability, so like the
Yeah, if it's all 0,
then it's not greater than maximum divided by the number.
yeah, it means that this never happens. So the minimum of the HIs is large. So we need to say that this happens with probability 1/6. So that's our question. This happens with probability 1/6. That's what we were showing. And so I want to bound probability that y is equal to 0. And this is bounded by probability that y minus expected value of y is bigger than expected value of y. So now it's just a simple exercise. We need to know expected value of x and variance of x. And so expected value of xi, it is equal to 6m over f0. Okay. The variance of xi, so it is like there is probability p of 1 minus p. So this is bounded by, so in particular it's bounded by p. So this is also bounded by 6 over f0. And so now we understand what is expected value of y. Note that some of the variables are identical if the AIs are identical. So we have to, we have to sum over all the set over all I for which we have different values, of course. So, so we have to choose indices. Better ideas to do it like this. Okay. And now y is equal for I equal. So for all I, such that so we sum over all j, such that there exists sum over xi, for which there exists j, such that ai equals j. So just we sum over all variables for which index actually appears in the sequence, right?
So you again change the definition of y.
Yeah, sorry. Yeah. So xi. So we sum over all the elements that appear in our sequence. So we sum over f0 variables. Oh, I can write it better. It's confusing in my marker. F0. So I sum over xi, for which I is an element of. So this is better definition. Okay. So I take a sum over all different elements that appear in the sequence. So I goes from I is smaller than from 1 till n. Okay, and so here we have for expected value, we will have f0 times 6m over f0 is equal to and there is no factor m here, it's a mistake. So expected value of y is 6. And the variance of y is also 6. Just because expected value and variance is the same and we have the same sums here. Okay, and now we can apply Chebyshev bound because here we substitute expected value of y, and here we have expected value of y squared. So it is equal to 6, or it's bounded by 6 divided by 6 squared. It's 1 over 6, and the proof is ready. Okay, and this is end of lecture. So we have proven this, but now the variables are only pairwise independent over which we take the minimum. So I just deleted v is just the minimum of these values, h applied to the sequence. So we proved it only using a minimal pairwise independent of hash function. And so we can use a hash function. So just take random a and b over field of size m, or something a little bit bigger than m. And then output h of x is equal to ax plus b. Okay, the details will be for next seminar, the last seminar. But this is idea. And so now there is, now we have proven an efficient way to estimate the f0 up to factor 6. The memory that we need is just the memory to store the hash function, which is 2, it's order log n. We just need 2 coefficients. I will explain next seminar where we just need 2 random coefficients of size log m, and we need to store the minimum value. This is even, yes, it's also log m bits. So we obtain this algorithm using log m bits. And now there are a lot of questions, like this is an estimation up to factor 6. What if you want 1 plus epsilon? And then I will explain that you can do this using 1 over epsilon squared, such estimations. So then we will have probability 2/3 with an estimate up to factor 1 plus epsilon. And then we want to approve factor 2/3. And this we will repeat as log 1 over delta times, and we take the median of our estimate. That will be the whole algorithm. But okay, this algorithm is order log m. And then the advanced algorithm with epsilon approximation will be log 1 over delta log m space. Okay, I talked too long again. So that's for, I will speak about it next week. And then we will start with lower bounds. But lower bounds is a difficult topic, so it will be for advanced topics. Okay. So then let's start the seminar at 8 again.